try and settle down as quickly as you can. So this class has never been this full before. It's like we have almost twice as many students as we did last year. And I'm not exactly sure why. I mean, obviously, it's just to do with changes in the composition and interests of the students we have coming in. I'm very happy that the class is so popular, but clearly it's putting some logistical problems on us at the moment. I don't want to. Obviously the first class is always different because this is add drop period, so people are still checking out which classes they want to come to. So if you can just bear with us for the next few classes, and then we'll see what happens. If we still have this problem that we haven't got enough seats for everyone, then we'll figure out something to do about it. But right now I don't want to, because it's difficult. Everywhere in campus we're having problems with classrooms at the moment. So I want to see what's really going to happen before we try and come up with something. One thing, yeah?
You have overflow in the next room if you'd like to use it.
We have overflow next room. What, I'm being carried live in the next room?
Yes, you are.
Okay, so yeah, thank you.
There's places to sit there.
There's a live video link to the next classroom if you want to go and sit in there, which of course is not nearly so good. But might be preferable for to standing. Okay, while we're here, let me just introduce Darwen. This is Darwen. He's a student in my lab, and he's going to be the TA this semester. He also TA'd this class last year, so he's an old hand at this. He was very, very well appreciated by students last year, so hopefully he'll be useful and helpful for you as well. And so he'll be dealing with the homeworks and stuff like that, and also he's available to, for recitations and to give you advice and stuff. So thank you, Darwen.
I have class.
Yeah, unfortunately, he has a conflict right now. So.
I just think I should show up in the first lecture and we can meet in an office hour or whatever.
Yeah, we'll figure out a time for his regular office hours. But okay, thank you. Great. Okay, so, all right, let's get into it. So this is digital signal processing. I'm Dan Ellis from electrical engineering, and so there are no. This classroom is full to capacity. There's a live overflow feed, video feed in the next room if you want to look, but if you can find somewhere to sit down, it's great. I've been teaching this class pretty much since I came to Columbia more than 10 years ago. And it's changed a bit over that time, but it's always been a class that I really enjoy teaching. And the reason is that it really feels like there's something useful to get across here. That DSP, digital signal processing, which is kind of a body of techniques and mathematics that was developed mainly in the 1960s, 1970s. So it's been around for a while, and it's quite well worked out now. It's sort of it's reasonably well understood, and its applications are very far-reaching. And so I feel like in this class, compared to I teach a class in speech and audio processing or in music signal processing, and that's sort of much more about the kinds of research we're currently doing. But in those classes, the things I teach are kind of like, here's something we've tried, not exactly sure about the best way to do it, but, here's what's going on. In this class, I feel like I'm pretty confident that when I'm telling you something, it's something that is actually, it's a good way to look at it, and it's something that's useful to tell you, which I guess, I don't want to undermine what I teach the other times. But this is, I feel, we're doing something useful here. What are we doing? Well, we're talking about ways of processing signals using computers. Signals are whatever, basically the kinds of things that come out of the real world, the kinds of things we measure that have some kind of use to us. That means they have some information in them, but the information may not be exactly how we want it. And so the idea of the tools of DSP is ways of manipulating the information in signals to try and make it more the way you want it to be, so you can do useful things with it. I assume that almost all of you have seen this stuff before, right? If you've had a double E undergraduate, then you have had Signals and Systems class, at least one, and in that class you will almost certainly have seen some discrete time stuff, seen the Fourier transform, seen the Z transform. That's pretty much all we do in this class as well. But when I advise students, incoming master's students, I often suggest that they give this class a go. And a lot of people who have taken this class in the past have had previous exposure to this stuff. It used to be, when I started teaching it, I was trying to cover more advanced topics. But I've kind of, over the years, I felt that the time was better spent really going over the fundamentals. Because for me, I took a class like this when I was an undergraduate, and I took it again in graduate school, much as many of you will be doing. And then I, started teaching it. And I feel like my understanding has gotten successively deeper. That it's like for me, there was a big gap between seeing the mathematics and saying, okay, I think I understand the equations, I know what's going on, and really developing an intuition, a deeper understanding of what exactly it means and how best to use these things. And that deeper understanding, that intuition, is the thing I really want to try and get across in this class, right? So maybe that, the equations you've seen are almost all ones you've seen before, but what I want to give to you is more of an insight into what they mean and how to think about them. And that takes a lot of time, in my experience. Now, different people have very different learning styles. Some people who have very sharp mathematical minds, for them, once they see an equation, they sort of get it, right? You're never going to learn anything more about it because the equation describes everything about it. But for me, my way of understanding things is much more intuition-based, and maybe that's kind of typical for an engineer as opposed to a mathematician. So for me, there's a lot more beyond the initial equation, and there's a lot of just sort of I don't know how to describe it, but having a feeling for how these mathematical objects behave, and how that relates to the practical problems that we can approach and solve with them. So that's kind of what's different about this class. As you'll see, there's a lot of stuff on the website. So if you want to try and figure out what's going to happen further on in the class, you can look at the videos from last year, and you can get a sense of how it goes. And you can look at the slide packs. But that's kind of the reason I'm doing it like this. I saw a talk a little while ago by a math teacher, actually a high school math teacher, who was talking about the difficulties of how to teach math and some of the problems of how it's done currently. And her point was that when we teach math in high school, we give people a lot of tools, but they're they can be completely disjoint from anything real or practical. And that was definitely my experience. When I saw calculus in high school, it was like, you can calculate the slope of these functions, and it was like, why? Why would anyone want to do that? And it comes like years later when you get into a physics class, and suddenly it's like, well, the gradient of these, fields or whatever is very relevant. You suddenly think, oh, okay, yeah, I guess being able to calculate gradients, being able to calculate slopes is very important. So the argument about this talk I saw was a much more effective way to teach this kind of mathematical material is to set up a problem, a real problem that has some kind of, that speaks to people, and then say, well, how are you going to do this? And it's like, well, we have this problem. We don't know how to get around it. And then you can introduce the tools, and then it's much better motivated. It's like, oh, I see. That's really useful. That's something. Now I can see why you'd want to be able to solve this, and you sort of motivate the work that way. So that really made a lot of sense to me. It's like, wouldn't that be great if we could teach everything that way? For various reasons, it's not as easy as that. I mean, it doesn't lead to a nice kind of logical flow in terms of developing the material. But I wanted to have a go at least starting off right now with some kind of motivational problem, which hopefully will start to make sense and will give me an opportunity to refer back to at various points. So for this first thing, I have this like ludicrously complicated setup, which I think is not such a great idea. But let's see if we can make it work. So the idea here is we're looking at audio because I deal in audio, and also audio is a great thing for demonstrating signal processing with DSP because it's one-dimensional. So what we have here, is this? Yeah. Okay. What we have is an oscilloscope, something simulating an oscilloscope. So I have some wires here coming into the audio interface, and then I have it's a stereo input, but I have two different channels. One is my voice. That's the top. The top should be. Let's just check that. So if I turn this down, if I turn the speaker off, no. Maybe this is plotted the wrong way up. Okay, so one of these channels is coming from this microphone here, and the other channel. Wait. The other channel is supposed to be coming from this microphone over here. Now that is the bottom channel. So why is the top channel not working? So if I disconnect this, okay, there you go. Top channel is the microphone, my microphone here. The bottom channel is this microphone over here, which is just a little distant microphone. Okay, now what we can do. So. And then if I make a sound like that's periodic, and so you see this is like the periodic oscillations of my vocal folds. And here you can see the other microphone is also recording a periodic signal, but it looks very different. And the point is that the signal reaching the microphone close to my mouth is different from the signal that's been bounced around the room that reaches the microphone over there. Okay. Now, what I want to for my next trick, I want to try and record this. So this is Audacity, and is this going to work? Okay, so let's just try that. Oh man! Audio input, audio output. Come on! Error opening sound device. Oh, sampling rate. Who knows? Let's try that again. Let's quit that. Quit. Audacity. Okay, quit that. Audacity. Sampling rate 16 kilohertz. I think that might be the problem, but it worked. It worked in the 1, 2, 3, 4. Okay. So this is supposed to be a stereo recording of the top and the bottom. And then let's try saving this. Okay, that's good. Save, although I should probably keep the previous one just in case this all fails. But there we go. Okay, so now I saved it, and then this is MATLAB. So I should be able to load this into MATLAB. And then we can listen to the two channels. So it should be, I read a stereo signal into MATLAB. And now if I play this one, the first channel should be the microphone channel. Internal device error. Yeah. Okay, let's try. This is things like that. There's no understanding what happened there, right? Come on. What? Sorry, docs, classes, E4810, 2013, MATLAB, session 1, MATLAB. Come on. 1, 2, 3, 4. Okay, that's something. 1, 2, 3, 4. They're different. Okay, so the idea is one's the and they're meant to sound different. They're meant to sound, one is supposed to be clear, and the other one's supposed to be kind of reverby and boxy. But all I heard was one is noisy and one is much less noisy, actually. But I guess I'm all right. Continuing on. we can look at these two waveforms against each other like this in MATLAB, and that's, oh man, look, no. That's not right. Maybe it's just because one of them is much stronger than the other. That's interesting. It's backwards. Let's. I don't know. So here are two waveforms that I read in, and the idea is one of them is they're different waveforms, and they've got different amplitudes, but they're different waveforms because they were differently recorded. And there's a delay between them because you'd expect there to be a delay in the different processing chains. And the problem then is to try and figure out how I can, if I only had the distant recording, here's the motivation. I've got a recording of someone speaking, I've only got the distant recording, I want to try and make it sound like I had a clean, close recording. So how can I regenerate the close recording from the distant recording? So how could I do that? Any suggestions from the floor? What's that? Use a filter. That's great. So the idea is, if I don't know how I'm going to do this, but this is what we're going to learn about. We're going to learn about building filters. If we could have some kind of filter, could take the input, which was the distant recorded microphone, which has got the voice in it, it's got the parts that we want, but somehow, tighten it up to make it sound more like the close recorded microphone. Then we could try and improve the quality. And so the question is, well, can we derive this filter? In general, this is a good training set, right? I've got a direct comparison between the signal I want and the signal I got. So if I can figure out the filter which does the best job reconstructing the signal I want from the signal I got, then that's the thing I should use in future. And so I can do this, and the way I can do it is basically by cross-correlating. Firstly, I whiten the input signal, and then I calculate the cross-correlation between the whitened input signal and using the same filter to whiten the output signal. I whiten them for reasons, I'll tell you what that means later on, and you'll see why this is what I have to do. And I'm estimating out to L points. L is, say, what is SR? Let's just check that, yeah. So L is 4,000, which is a quarter of a second at the sampling rate of 16 kilohertz. And then if I plot, there we go. This is the actual, that's not right. That's definitely not right. This is the cross-correlation between the two whitened signals. And, well, this is the delay, and we see there is a significant delay in here. This is where 0 would be, and so it's delayed out to 80 milliseconds or so. But it's not supposed to look like this. It should be not symmetric. It should be like going out, and there should be discrete echoes. When I did this just now in my office, it would look much better. So, but the idea is this is sort of like an index of how every moment in the input relates to a moment in the output, and it's saying, well, the information that comes out of the input appears in the output this much later, and with these kinds of patterns. Yeah.
Is should symmetric or shouldn't symmetric?
It should not be symmetric. Yeah. Again, this is just an illustration. We'll go through all this stuff in a few weeks' time. But the idea is, if I had this and it would work, then I could estimate an inverse filter like this, maybe, and then I could actually reconstruct a version of X by taking my estimated filter and applying it to my original filter, right? So here's my original output, the distant mic output. I'm using this estimated inverse filter to generate a version of XR. So now the original X sounded like this. I don't know what this is going to sound like, actually, but this is the original X again.
1, 2, 3, 4.
And this is the reconstructed based on the output Y.
1, 2, 3, 4.
Imagine that one sounded like, oh yes, that sounds more like the original than the decimal one. Yeah, I think there's some problem with my setup, but that's the general idea. So here's But here's the point. Here's the bottom line, right? This is a real situation, right? We definitely, I don't know if any of you ever tried like recording lectures or something like this. It's amazing how when you're sitting in a room, this is kind of one of the things I do research on, but like you're sitting in a room, someone's talking at the front, you have, you know, unless the room is really bad and really reverberant, you're pretty good at understanding what they're saying, and you kind of feel like you can hear what they're saying independent of what's in the room. If you make a recording, you listen to it, it's like suddenly there's all this noise and boominess, and that's because, you know, we're really good at using our ears to differentiate between the direct sound and the reflections coming from the walls. But when you have a recording, suddenly it's not set up in the right way, so that those things become much more apparent. And so this kind of setup where you could actually figure out a filter to try and separate those things out, not just equalizing, but actually if you get it right, you can actually cancel out the reflections. Then this could be something that was really useful. But it's not obvious how to do it. So there was one other thing I wanted to show you. Let's see if we can make this happen again. So here's the oscilloscope again. And then this, like I say, this is a crazy, crazy setup. But okay. Okay, so I used a little PD there to generate an ideal waveform from the computer. This is what was playing out, which is a ramp waveform. And this is what's being recorded by the microphone, which clearly doesn't look anything like a ramp. Like, you know, you could say, well, I know how to do this problem. I'll just play every possible voltage out of the speaker. Then I'll figure out what voltage was recorded on the microphone and just build a mapping. But you can see, well, it's not a one-to-one mapping. And the problem is, of course, it's not instantaneous, right? The voltage here has an effect on all these different voltages out here. So this is not going to help us. But if instead of playing a ramp, I'd used a sinusoid, then lo and behold, the sinusoid being played output, the input, the recorded input, is pretty much a sinusoid. It's got some noise in here because, like, it's actually recording what's in the room. It's not just recording what resulted from the speaker. But first order, certainly compared to the ramp waveform, we get a sinusoid out. We put a sinusoid out. We get a sinusoid in. And this is an illustration of the idea that sinusoids are the eigenfunctions of linear systems. That is, that if you have something which is linear, and it turns out the air in a room is, you know, it involves distortion, but it's very linear, then when you put a sinusoid into a linear system, the output of the sinusoid is shifted in amplitude, it's shifted in time, right? You can see there's a phase shift or a delay, but it's still a sinusoid. And if we change the frequency of the sinusoid, you know, different things will change here. Oops. In particular, the relative amplitude of the output and the input will change. And indeed, the phase also changes, the phase shift. But the fact that it's a sinusoid still remains the same. And that's the critical thing. So one way we can actually figure out this filtering problem is to play out a series of sinusoids, figure out the exact modification of gain and phase at every sinusoid, and use that to modify a signal. Then if we played out a sinusoid, if we recorded a sinusoid, we'd be able to look up the sinusoid and figure out which one to play out. But it turns out by using the Fourier transform, we can decompose any signal into sinusoids. We can modify each one, and that's actually how we can solve the problem. Okay, so that was the other thing I wanted to demonstrate here. Because I'm never going to get this setup working again, so I better do it now, right? Okay. All right, how did you like that? That was my effort to try and motivate this. So in general, when possible, obviously, it's nice to use that kind of demo, and I like to do these demos in class, but I'll be using MATLAB to demo stuff fairly regularly, but not most of the time. Most of the time, I'll just be talking through these slides. Any questions or comments? Okay. All right, so what are we going to do today? What's left of today? My first slide pack, which will take us like this week, today and the next couple of lectures to go through, is very introductory. It's just trying to make sure we're all on the same page. I'll start off with some basic material about logistics of the class, and then I'll talk, just make some very broad definitions about what's going on, again, just to synchronize us. Okay, so digital signal processing, modifying signals with computers. I guess I kind of already talked about that. There is a website. It's on my website. Hopefully, yes, we can go here. So if you go to my homepage, which you can get to through various places, it's just this link here. And then there's a bunch of stuff on here. This is hopefully has, however unslick it is, it's still got the information you need. So go here, and in particular, it's got the course outline, which is the map, the syllabus of what we're going to cover. What we've got here are links to the actual slide pack. So the slide pack that I'm using today is right here. Is it? I think it's still from last year. I haven't updated it, but I'll update it. If I modify the slides, I'll probably make some small tweaks, so I'll modify them. But it's got last year's content for now, and it's also got the videos that I made. So I'm making the video of this class, and so these videos will be uploaded shortly after class. They're not, not anything special in terms of production values, but it gives you a chance to review stuff. If you missed something, you can go back and look at it if you want. And we've also got other stuff down here. The MATLAB scripts here on this page, I try to put in the actual scripts of what I did. So here is like the demo I just went through on MATLAB, trying to recover the filtered signal. So, and then some other stuff that I'm going to show later on. So you can check out what I do in MATLAB and try it at home if you want. Here are the routines that I used. The problem sets will be assigned on here. This week's problem set is already posted. These are questions from the textbook. This is the textbook, Mitra. I'm using the 3rd edition, which is published a few years ago now. There's actually a 4th edition out, but it's easier for me to stick with the 3rd edition rather than trying to go through and change all the references. I didn't see any particular need to switch to 4th edition. I'm worried that one year it's going to be like, well, you can't buy the 3rd edition anymore. You can only get the 4th edition. Let me know if that's a problem. But right now, this is the recommended textbook. And then the problem sets are referenced as questions in this textbook. So you need access to it, at least to figure out what the question says. This week, I've scanned in the questions because I know that people may not have the textbook yet. But in the future, I'll just be assuming that you can look them up and get them. So it's assigned on Wednesday, and then the problem sets are due the following Wednesday in the Wednesday lecture, and we'll collect the problem sets at the end of class. So you should bring them in, drop them here, and then we'll take them away and grade them from there. There's some information on projects. It's kind of very wordy and not all that. All right. There will be some information on projects. And there's some information on the exams. When we get to midterm and the exam, I'll put some information up on there. I don't know what happened with that projects page. That's weird. Oh, here we go. So yeah, there's... Okay, I'll check that that's working. The website was down over the weekend, which was kind of like classic. Okay. So... interesting. That's not it. There we go. Oh yeah, one thing on the website. It has my information. These are my office hours, Thursdays 2 to 4. This is Darwen, the TA, who we just met. Last year, his office hours were Tuesdays 1:30 to 3:30, which worked out well if people wanted to ask questions about the problem set, which is due on Wednesday. I haven't checked with Darwen what his schedule is, whether he can make that. But would that time work for people here? Is there a conflict with that people are taking? There's always going to be some conflicts, but it's not easy to tell if there's going to be a major conflict.
Question.
Yeah.
So if the class size remains this big, are we still going to have one-to-one TA?
That's a good question. Are we going to stick with one TA if the class is this big? Maybe not. It's difficult. It's just the way that the TA slots work. It's not easy for them to magically create another TA at this point in the year. But clearly, we've got to do something exceptional. So we'll see. We'll see. Certainly, if it becomes a problem with, that you can't get time with Darwen because you need to, then I'll make sure that we do something. Okay. All right. Well, if there's I'm seeing some people looking a little bit stressed. If there is a time with this, if there's a problem with this time, then send email to me and Darwen, maybe suggesting a better time, and we'll see if we get, or telling us what the situation is, and we'll see if we can figure out something better. And I'm not even sure if this time will work, because like I say, we have to fix that with Darwen. Okay. So the grading structure, grading is part of the deal here, that at the end of the semester, at the end of the course, you're going to get a grade. I never feel that comfortable about it because I'm not really about trying to judge you. I'm about trying to teach stuff. But here it is. We have the homeworks. They count for 20%. The idea is that you can get 100% on the homeworks. The homeworks is not about trying to assess your progress. The homeworks are really an integral part of the learning, that they give you a chance to try out the stuff that we've spoken about in class, and that is pretty important because you can have someone tell you something and you sort of feel like, yeah, I understand that, but until you actually try it, you don't know everything about it. You actually have to go through the process to sort of get the feelings. That's really all it is. It's just like one question on each of the major topics, just so that you've actually used it and you can see how it works from the inside. Questions coming from the textbook, Wednesday to Wednesday schedule. All research shows that studying any kind of material as a collaborative, as a social experience, is much more effective than studying on your own, right? Because if you're studying on your own, if you don't understand something, you sort of look at it for a while and like, okay, that's as far as I can get with it. If there are several people and you can talk about it, then, firstly, if you get stuck, you can get past that much more quickly. Secondly, you can share different perspectives, and that's always the strength of understanding something, is to understand it in multiple ways. So I highly encourage you to form study groups or work together on the homeworks. But so there's no issue with like, well, is this 100% your own work? No, I don't mind if it's something that it was ideas you got from someone else. But obviously that doesn't extend as far as simply copying, because if you just copy your homeworks, then you're not getting any benefit. We're not going to try and police this at all, right? Whatever you want to do. But I'm telling you, the point about the homeworks is to help you learn the stuff, and so don't cut out that part because it'll impact your experience. We collect and we grade the homeworks, but the only reason is just to give you a little incentive to actually do them, right? I know what it's like. I know that things get busy. And so for me, it would always help to actually have a deadline and have an obligation to do something. And so it's slightly, it's a bit nominal, but that's what's going on here. There'll be a test in the midterm test, which will be just like one session where you have one question to work through, a sort of slightly elongated question. This will be more tricky, I guess, diagnostic rather than educational. So that'll be 20%. People sometimes do badly on the midterm. It's not the end of the world. Don't be discouraged if that happens. And then at the end of the semester, this is where the bulk of the points come in. We have a final exam, which is like, full 3-hour thing in exam week with a number of questions. And again, they're sort of like the midterm question. They're a bit more probing and difficult. And then we also have a final project, which is has equal weight as the final exam. It's a bit, it's a bit much to ask you to do all these homeworks and the final project. So the final project doesn't have to be huge. It's like maybe 2 or 3 weeks worth of work in terms, 2 or 3 weeks worth of homework, something like that. But it is really useful for me in terms of figuring out exactly what kind of command you've got of the stuff, and hopefully it's more interesting and rewarding for you than just typical exam work. So that's something that sometimes I end up grading these, over Christmas break, and normally it takes me longer than I would wish, and I'm sitting there, and everyone else is enjoying Christmas dinner, and I'm upstairs grading these projects, and I'm thinking, is this such a good idea? But if I dropped this, I'd feel like the class was really not meeting the aims of like trying to give you this intuition that actually working on a project where you get to do something which is, not just from a book, but it's something completely new and open-ended. I think that's a really good way to learn about the stuff. So I guess that's what this slide is about. So the guidance for the project is, I want you to actually do something that involves taking a real signal and processing it with some goal in mind, trying to achieve something. To give you that experience of like, well, okay, we've learned a bunch of theory, but there are all these practical aspects which don't really lend themselves to classroom presentation, which you are going to have to deal with in any kind of real-world experience. And so here you can have a go at doing that. Normally I recommend working in pairs or working on your own. If the class stays this big, I'm going to strongly encourage you to work in pairs or even in groups of 3 just to, streamline the total number of projects that come up. But the idea is it's, relatively individual, small-scale thing. I grade it based on a report, but I don't want the report to be super long. I just want a brief report that basically gives me the information about what was interesting, what you did well. In the final week, we have some presentations. Those are completely optional, but just sometimes people, just enjoy talking about what they've done. And this is always a lot of fun. There's always a really interesting range of projects that come up. I strongly recommend using MATLAB. So that's what I was using there. I assume everyone's, okay, hands up if you've used MATLAB before. Great. Hands up if you've never used MATLAB before. Okay. Right. The peer pressure is overwhelming here. It's like, what, you mean you've never used MATLAB before? I hope that means that you've all used MATLAB before. If you haven't, don't panic. MATLAB is very easy to learn. I think everyone would agree. It's kind of, the reason I'm recommending it is because it really is very much a sweet spot for doing this kind of thing. It's very, it cuts out a lot of the unnecessary stuff and lets you just directly talk about applying DSP algorithms and manipulating signals. So it makes it much easier to work with on this kind of thing compared to, say, implementing in C where you have to worry about memory management, etc. Recently, in the past few years, I've been using MATLAB almost exclusively for the past decade. In the past few years, the students in my lab have started using Python and NumPy and SciPy, and it's a very strong competitor to MATLAB. If I wasn't so heavily embedded with MATLAB, I would want to change. And I've been trying to, one of my projects last summer was trying to make the move. I'm sort of mid-transition, but certainly for the purposes of what we're doing here, MATLAB is still the best solution. So that's why I recommend it. There was that page on the website, which may or may not be working, but I'll make sure it is working. It has a bunch of just ideas. They're not the greatest ideas. I've had problems with people finding trying to stick too literally to those ideas, and it's much better if you come up with something. The ideal project is something that where you sort of you're in class, we're talking about stuff, and it sort of suggests to you, it's like, I wonder if you could do this with it, and this is something that matters to you, speaks to you. And so if you have an idea like that, and then you talk to me or talk to Darwen, and we say, okay, well that typically this may be something impossibly hard, right, or something very difficult. But we can say, well, okay, that might be a little too ambitious for a project, but you could do this part of it. You could cast it this way, and then we can come with a project which is both the right scope for the class, but is something that is like actually interesting to you and something that can tap into that kind of motivation. That's the best thing. So it's the best thing is if you can bring something which is something personal, something that actually excites you, then it's going to be much easier to get stuff done. Yeah.
Does the department still have the license for MATLAB that you can send a link?
Yes, I believe so. So does the department have a license? As I understand, Columbia, the university, has a site license, and so maybe it's just C's, but yeah. So if you follow this link on the website, it tells you how to get hold of it. You can download it all, and by virtue of being students here, you have the right to run MATLAB. So that should not be an issue, right? Okay. Finally, okay, again, I'm sorry to have to say this, but I have in recent years had some problems with people who end up, copying projects from the web. In part, this is a problem because I make it so open-ended that it's like, okay, you can choose anything. And like, oh, here's this nice project which seems to be kind of the right kind of thing. I could just submit that. People don't always get away with this. I don't know how many people do get away with it, but I know the number of people don't get away with it. So, because it's often, it's kind of, it shows, right? Just because you can just tell. I guess the ones that I catch, you can tell. But again, it really defeats the whole purpose of being here, right? If you're not going to do the project, then why are you here at all? So obviously, I know none of us at this point are thinking that way, and I understand that by the end of the semester, things can get a little more desperate, and so people might be tempted. Please don't. If you are in that situation where you're feeling like, oh man, I don't know what's going on, how am I going to get this project done? I've got all these things to do. I'm so willing to try and find some other way around it. Like I'm not going to be at all. I mean, it's dangerous to say this, but I'd much rather have a project at some longer, more appropriate schedule rather than on deadline than have you do something which you don't feel good about in terms of putting the project together. So we'll talk about that towards the end of the semester, but I'm really interested in you doing the work and having the experience and learning. So please work with me on that. One of the issues here actually is that there's a gray area, right, between like, well, I'm interested in this project. There's this project here which I found on the web, which is kind of similar. Are you saying that I can't use that and I have to like re-implement everything myself? And that's not a very realistic experience. Certainly, if there is something which is a useful basis to work from, then that's fine. But you have to be very, very clear about which parts you're starting from, which parts are your own contribution. So it's fine to use stuff as long as you make it clear to me what you've done. The gray area, the crossing the line, is when it's like I'm reading it and it's like, oh wait, who actually wrote this code, or where did this code come from? And again, it's amazing. I spent a bunch of time on this kinds of forensics, and it's kind of interesting in its own right, but I'd rather not do it. Okay, so some of the kinds of projects we've had in the past. There are these examples on the website of the actual reports, and they're very varied. The style of the report, the style of the project, huge variability. That's fine. It doesn't have to be at all uniform. But so some of these, which are kind of audio-related ones, so they're naturally most interesting to me. Solo singing detection, so taking a signal, which is like some music, and then there are points where it's just the singer alone. Can you figure out where just the single singer is? That was very cute. That actually, I think we turned that into a paper and published that. Guitar chord classifier, so playing an chord, trying to figure out what the chord is or what the notes are. Speech-music discrimination, this is a very long-standing problem. Just if you have like a recording from the radio, you want to tell where the DJ is speaking versus the music, and you can use various different kinds of signal processing techniques to try and come up with features. Someone a couple of years ago did a sonar thing where they would play out a signal, record it in, and then try and figure out something about the shape of the room based on the reflections. There was this guy who did this project on construction equipment monitoring. He was in civil engineering, was interested in just how much time a machine, maybe it was environmental engineering, sorry, I forget, but he was interested in like construction machinery, how much time does it spend idling as against in use, and so he just put a recorder on a machine, recorded like, an 8-hour work day, and then using the signals that are coming in, he could tell the difference between when the engine was on, when the engine was off, or when the engine was on and the machine was under load or idling. And so they're all, really fun things. these are some of the ones that are listed on the project site. The DTMF decoder is like an old standby, which is touch tones, figuring out what frequencies are there and converting them to numbers. Even that, though it's a pretty well-constrained problem, it still brings up these issues of like, well, how do you deal with noise? How do you decide whether there's really a signal there or not? And so how robust is your signal to added noise, your system to added noise? Reverberation, we'll see later on. There's this very simple effect where you can basically use linear convolution. It sounds like reverb. And so there are various things to try and simulate that studio effect, although it's difficult to evaluate. Compression, yeah, I mean, obviously that's a big application of DSP, that is to reduce the amount of data that's used for a signal. But again, it's typically there are compromises between compression ratio and signal distortion, and they're kind of difficult to quantify. So anyway, we'll talk more about the projects later on. I mean, we don't really have to start worrying about the projects until, say, after the midterm, something like that. But hopefully this is going to be a fun and a rewarding and useful part of the overall course. Any questions about that? Okay. MATLAB, okay, as I said, sorry, I guess I already talked about this. I like MATLAB. It's the right thing to use. We'll be using it as part of the homeworks. The homeworks will typically have 1 or 2 MATLAB questions on as well. You're not going to learn, very much MATLAB programming from solving those homework questions, but just to make sure that you have some sense of how to get it working on the computer. And we have the site license through Columbia now. So here's my effort to sort of draw the entire syllabus of the class in a kind of flow chart, and a sort of mind map flow chart. So we start off with the general idea of discrete time signals and systems. So this is working in the time domain, that basically, we're thinking about the signal as the voltage that you might see on an oscilloscope, but now it's an oscilloscope that's being implemented by a computer, so we have a set of discrete samples, and that's the discrete time part. And compared to classic signals and systems, which sort of assumes continuous time, then basically this whole sampling in time really kind of produces a bunch of, I think of them as artifacts, right? I think of them as things that mean that you're thinking about it in continuous time, but it isn't quite continuous time. We have to get that straight, because that's what we can actually do. There are different perspectives. You can view discrete time processing as a completely self-consistent set of operations in itself. But for me, I was taught, coming from an analog perspective, and I find that that's what the world is. The world is the things that are coming out of microphones are analog signals. And so for me, it's like discrete time is an approximation to continuous time, so we have to learn the limits of that approximation. We'll learn about the ideas of systems, the ideas of taking signals and processing the systems. So then in week 3, we get onto Fourier domain, which is talking about not viewing the signals as functions of time, but as functions of frequency, as functions of the Fourier variable. And of course, this is this beautiful piece of mathematics where a signal is equivalently described in either domain. There's no privilege between the two. They're just different perspectives on the same signal. And if you boil signal processing down to its very core, this is it, right? It's thinking about a signal as a set of frequency components rather than as something that changes with time, and then that allows you a totally different way of thinking about processing and modifying the signal. So once we define the Fourier transform, then we talk about the discrete time Fourier transform, which is what happens when you use this on sampled signals. And then that leads us to the Z transform, which is this generalization of the discrete time Fourier transform. Discrete time Fourier transform is it's got some odd properties. And the Z transform shows that the DTFT is just this particular case of this two-dimensional transform of the signal, which in itself is like a very strange concept. But when you understand that the DTFT is just part of it, it makes the DTFT's properties much easier to understand. And so it's this is kind of like the most abstract part of this approach, which is we're going to introduce this thing whose role is merely as a way of understanding the part we care about. We're going to introduce this whole space of things that kind of don't that we don't really use, that don't exist, or they exist, but they don't exist in practice, just as a way of understanding the thing that we do care about, the discrete Fourier transform, or discrete time Fourier transform. Okay, so that's the sort of theoretical basis. And then from week 5 onwards, we start looking at how to use this in practice. So we talk about systems, and now we're able to analyze these systems using these new Fourier and Z-transform tools. Then we get onto the specific details of filters, which are the things we can build, these systems, these linear time invariant systems that take signals out, generate signals as output, take signals in, generate signals as output, and then have modification to the information in the signal in some useful way. There are 2 big classes of filters we'll talk about, FIR, finite impulse response, and infinite impulse response. So we'll define the basic space of these filters in weeks 6 and 7, and then in weeks 8 and 9 we'll talk about different techniques for designing these. So this is now basically practice. You know, here are the actual tools that we use to design these in practice. And so you could, you can open up a textbook and you can get this. And you can go to MATLAB and you can type in, whatever it is, FIR, PM1 or something, and you can design a filter straight off. But the point here is to understand what's going on when we do this, and in particular, what are the constraints and limitations? What kind of output can we get when we use one of these tools? And then, as practicing engineers, we can use these tools that we'll learn about. We don't have to do all this detailed analysis, but we'll know what's going on, and we'll know when things go wrong. We'll have an idea of where to look. In week 10, that's the sort of the main flow of the course, and then at the very end, we look at a few other topics. We look at the fast Fourier transform, which is just this kind of algorithmic trick for calculating the discrete Fourier transform, the discrete time Fourier transform of a finite duration signal, calculating it with high efficiency, but it's like it basically revolutionized what you can do with DSP. So it's a very, very elegant and sort of beautiful piece of algorithm. So we'll cover that. And then at the very end, we'll talk a little bit about the interface between discrete time and continuous time, basically the problems of sampling and reconstruction, which again, are practical problems that may come up. But that's all we're going to cover. And my guess is that probably most of that you have seen before. But like I say, the difference is emphasis. I'm going to really try and not just show you what the definition of Z-transform is, but motivate why we have it, and hopefully at the end have you feel like, okay, I see why this was a good solution to reaching the goal. The goal being being able, for me, the Z-transform is like, it's wonderful because you can instantly, you can have this filter, which is a bunch of numbers. You can look at it on the pole zero. You can look at its pole zero diagram on the Z-plane, and you can totally immediately see what kind of filter it's going to be, how it's going to behave. And that's where I want you to be by the end of the class. Okay, any questions about that? And like I say, all the slide packs, at least last year's versions of them, and the videos of the lectures are all linked to the website on the course outline page, so you can see what's going on there. And also on the course outline page, it lists the different sections of Mitra, which are the relevant parts of the textbook to each section, to each week. Okay, so we have 20 minutes or so left. Let's just get going on some of this basic material. Like I said, we're still not going to do anything terribly complicated, but let's just sort of start talking about the concepts and getting our minds into the right place to what we're going to talk about the rest of the semester. So digital signal processing, signals are things that vary with some dimension, for instance, time. So a function of time, and they've got something in them, they've got something useful in them, some information. Information is a very, malleable term. But there's something we care about in the signals that we want to be able to manipulate, we want to be able to detect or modify or maybe remove. And digital signal processing is the mechanism by which we're going to do this. So for me, the prototypical signal is what a microphone records, the variation in air pressure at some point in space. That's what a microphone records. That's what sound is. And so we can think about it as P of t, so it's a function P of an argument t time argument. Of course, you can have higher dimensionalities. So an image, a grayscale image, a picture, is intensity is a function of x and y, or some kind of way of mapping over 2 dimensions. And a video signal is now, a monochrome video signal is time varying, so it's a function of x, y, and t. And then a video signal is basically 3 different monochrome signals for the R, G, and B channels. Turns out, just with 3 separate intensities, you can provide the color that we perceive. But, so you can have signals at different dimensionalities. Maybe we are going to be entirely limited to one-dimensional signals in this class. In 2 dimensions, which is image processing, most of the concepts are the same, but it turns out that the things you can do are kind of more limited, I would say. And so it's actually, basically it's a subset of what we're going to cover. Now, there are some aspects of what happens when you put into 2D that, you have to go through. But it's still filtering, and it's still basically the same things. It's just with more dimensions. It just gets much more complicated the math gets more complicated. So hopefully we're not losing anything by focusing on one-dimensional signals. Examples of signals. These are just to get us thinking. Noise is a kind of signal. Noise, again, is also a word that has a lot of different meanings depending on what you mean. You can think of a signal as being composed of information and noise, and they're totally subjective. Information is the part you care about. Noise is the part you wish wasn't there, that's making your job harder. Of course, you can also talk about noise as, white noise or something, which has a mathematical definition, but it just means there's something that's unpredictable, something where knowing what happened in a signal up until a point doesn't help you at all in predicting what's going to happen as the signal evolves. Other kinds of signals, well, obviously, sound is the one I care most about, but another one-dimensional signal, another signal which can be represented one-dimensionally is radio. Like, instead of the pressure at a point, it's the magnitude of the electromagnetic field at a point. Not my strong point. But there's a lot of signal processing which goes now in wireless communication, which is, ways of dealing with the signals, but instead of being at, 1 kilohertz, they're at 1 gigahertz or something like this. But it's still the same idea of filtering something in time. A lot of signals that come up from biological processes now, and this is also a big area. There's a lot of imaging work in biomedical applications, but there are also things like, electrocardiogram signals or electroencephalogram signals, which are basically, sensors. You have a little electric field monitor on your head, and you can pick up stuff that's going on in the brain. And these, are, again, they're huge problems in trying to separate signal and noise there, but very, very interesting results that can come out. Music is another sound signal. We do a lot of processing in my lab, a lot of work with music, because it's like a very interesting problem of like, well, what is the information here? Why is the signal like this? And it's just fun to work with. Image and video, one of the things you can do with images is trying to compress them. A raw image or a raw video is a very large amount of data, but it turns out that a lot of that data is not that important to a viewer, and so you can try and figure out how to, make your videos fit onto a smaller file. These are the kinds of things. Any other suggestions? Things that people feel should be on this list? How many people here are from biomedical engineering? Okay. Hi. I'm glad to have you here. There's always a few, because I know that the people who are working on the imaging track there, I think, this is a recommended class, right? Yeah, so that's always fun, because, that's typically the projects from that area are in a different domain than the things I normally look at. So are there any other people? Are there any people here from civil engineering? Okay, yeah, so we get some people from civil engineering again, because, these kinds of ways of analyzing, I don't know, in the past, the people who've come have been looking at things like, okay, I'm looking at the motion of this building, which is essentially there's a signal here, which is how this thing is moving, but then there's how the bottom of the building moves compared to how the top moves, and thinking of that as a system. And so there are lots of different places we can get signals, lots of different things we can try and do with signal processing systems. Okay. Signal processing, so that's signal processing is modifying the signal to rearrange the information, which, you can have all kinds of motivations to do that. Signal processing as a kind of separate discipline, its origins were in the mid-20th century. Things like radar. Radar was like magic, right? It was like, this was during the Second World War. We had this problem of trying to be able to detect airplanes coming in the dark. You couldn't see them. Up until then, people wouldn't fly in the dark because they would, get lost. But now it's like, okay, they figured out how to navigate, but you wanted to be able to find these things. And so you can send out a radio wave, and there's going to be a very faint reflection reflected off the metal body of the plane. But if you do it right, you can actually pick up that reflection. It's going to be very noisy, but you structure the signal so that it's got a very narrow frequency band, so you can separate it out from noise by using a filter. Then you can figure out the timing, and you can figure out where these things were. And this, had huge impact. But it was like people starting from doing this, they didn't have any kind of theory behind this. So the theory of trying to use Fourier transform, which had been around, for a couple of hundred years, as a way of analyzing this was developed, and that's where this stuff came from. And then, of course, as our ability to do more and more with electronics, and now with computers, as that grows, then there are more and more applications where this is something useful we can do. So, the problem, the radar thing, which is basically you send out a pulse of energy, and you get a very weak reflection back, and you want to figure out how long it took, because that's how far away the target is. That's a problem of separating out the noise. Basically, you're going to have something which is just going to look for a threshold. It's going to look for energy at this frequency, but you have to make sure that you've filtered out enough of the random background so you can actually see on the threshold where this pulse is. So that's kind of like the classic application. Data compression I mentioned, which is if you have a signal which is, whatever it is, the sound signals we were looking at were 16,000 samples per second, they can add up quite quickly. But it turns out that, well, that's not, that's more data than you need. And so if you can figure out exactly how to separate out the parts that you need from the parts that don't matter, then you can reduce the total amount of data you have to store on disk or transmit over a link. Representation for recognition and classification. This is kind of what a lot of the research that I do. I do things like speech recognition. I mentioned we're doing this music analysis, trying to do things like, transcribe the notes being played in music. This is, signal processing is only part of this, right? So there's another part behind that, which is some kind of machine learning or pattern recognition. But usually, with any kinds of those tasks, the signal processing is a critical part that limits the performance of what's going to happen afterwards. And so you have to get this right. There's no point in trying to recognize a pattern if the signal you're working from has got so much noise that the pattern is, very, very hard to distinguish. And so often you can, there's been huge developments in machine learning in the past 10 years. But if you have a good insight into a project, into a problem, and you can apply the right kind of signal processing, then you can, have impacts on the overall task, which are much greater than the differences between, last year's machine learning algorithm and the new one. And so you have to get these things right, and you have to know these things. So there's an interesting sort of field now, which is like people who are trying to combine expertise in signal processing and machine learning, because you need people, you need experts who can do both to deal with a lot of the interesting problems that are coming up now. Okay, so that's signal processing in general. Now, digital signal processing is this idea like, okay, signal processing, these 1950s radar systems are using analog electronics. It's continuous. The signal is being represented as a voltage on a wire, and there's essentially no limit to the bandwidth. There are practical limits, but there's no granularity to what we're looking at. And so this is like a continuous time signal here, which is also continuous in value, right? Because it's a voltage, which you can measure it however finely you want. There's always still more detail there. To get from this to something that we can handle on a computer, there are two things we have to do. Firstly, we can talk about either order. The simple one to understand is the idea that we're going to discretize the value. Now, the computer isn't dealing with voltages; it's dealing with binary signals, ones and zeros. So a number, a variable intensity is represented as some kind of quantized number, like 16-bit number or a 64-bit floating point number or something like that. But at the bottom level, there's a finite set of different values it can represent. And so it's taken this continuous axis and it's broken it up into a set of different steps. There may be cleverer ways of doing it than uniformly spaced steps, although it turns out that that's what we usually use. Typically in audio, we'll use 16-bit sample, which is taking the voltage, breaking it up into 65,000 different individual steps, which are uniformly spaced, and that gives us enough detail of the signal that listeners can be satisfied. So that part's obvious, that we have to represent these numbers in finite length, binary numbers. But that isn't enough, because we also got this problem that, well, what about this continuous time? That here I can put a signal through a quantizer and get a continuous time signal, a signal in time that only takes on a set of discrete values, but the transitions are still at arbitrarily precise time moments. So the other thing we have to do is we have to sample in time. And this is, like I say, this is where the problems come in. Because basically, again, you could think about doing this in multiple ways, and there's interesting theory about doing it in non-uniform ways, but here we're going to assume we do it uniformly. So we have some clock that every t seconds, where t is like 44 microseconds or something, we record the actual level in the input, and that's this number we store. And so if we do both of those things, we end up representing this continuous signal as a sequence of quantized values. And so here, to perfectly represent any signal, 1 second's worth of the pressure at a point in time, that's an infinite dimensional signal, because it could be like the pressure is varying, a million or a billion or faster times second, and we have to represent all this. But here what I'm going to say is, well, I'm only going to look at the signal every 44,000th of a second. I'm going to store the value there. If things happen faster than that, I didn't get them. That's a lose. And then each of those values, I'm going to quantize some number of bits. And so now I can take that 1 second of sound, I can store it as 44,000 16-bit samples, 88 kilobytes of data. And I'm done. I got something I can load into MATLAB, have on my computer that I can process, and I'm ready for digital signal processing. The problem is, what happened in those wiggles, right? What happened? What was the impact of only recording this signal at certain discrete times? And it turns out that it's pretty important, because clearly if I only stored the voltage once every second, I wouldn't have very much information. I wouldn't expect to be able to recognize what the sound was or anything. So it's like, okay, well, I need to do more than that, but how much more than that do I need to do? And what exactly am I sacrificing? So that's the deal with DSP, is that we're able to analyze exactly what is happening, what the limitations are, and thereby make the right choices in terms of the sampling rate, so that we store enough data, we don't end up storing too much more data than we need to, and doing something that's inefficient. So, traditionally, I guess pre-1970 or something like that, or I guess even gradually, there was a transition from analog signal processing to digital signal processing, maybe between 1970 and 2000 or something. Traditionally, you'd have a system like maybe with some transistors and resistors and capacitors, would take some kind of input signal, maybe a voltage, would have some processing going on with some op amps, and generate an output signal of voltage here. Of course, we still have these, right? I mean, at the end of the day, there's still voltages coming out of the microphone element in that recorder. Oh my God, it's still on. But what we do now is we take it and we translate it into a digital domain as quickly as possible. So we get this discrete time representation. We then have our discrete time processor, which generates a discrete time output, again, a set of sampled values in time. And then if we have to put them back into the real world, we put them through a D2A converter to convert a sequence of signals back into a continuous voltage, which we can then put into a speaker or render on a screen or something like that. So, we've got this processor, because the processor is different, right? Here it's analog input, analog output. Here it's discrete time input, discrete time output. But we can basically try and do the same thing as close as possible. And so we can try and simulate something like this with this entire loop with the analog input and analog output. Although in most cases, we won't be able to simulate everything, just because we're going to have this limitation of the frequencies of what we can handle. what are the strengths and weaknesses of digital processing? The real driver for digital, certainly in audio, is about noise performance. So think about how music was distributed. Originally, it was the first wave of popular music was vinyl discs, and there the signal, this variation in time, is represented as actual variations in the depth of a trench carved into the surface of this plastic disc, which is it's kind of nice. It's a clever technology because it allows you to have an hour's worth of audio on this fairly low volume thing, and you can build the transducers and you can make it very high quality. But it's not that reproducible. That if a little bit of dust falls into the trench, then the thing that's trying to pick up, the little needle that's trying to pick up the size of the trench will get jogged and you'll get noise, and then there'll be wear and things will happen. Digital signal, once you've got a sequence of numbers, the whole point about digital electronics is like, well, I'm only going to think about two values. If I have a little bit of variation about those values, I still know which bin they're in. And so until things get really bad, everything stays the same. And so once you've got a digital representation of a signal, you can essentially reproduce it perfectly the same. You can propagate it. You can distribute digital copies. They're always going to be perfectly the same. Of course, they're not perfect because they've got this quantization. But if you set the quantization small enough, then you have this fixed level of noise, which never gets any worse. One of the nice things about DSP is that you can implement them using a general-purpose computer, which means that you can have one processing element. Not general-purpose, but you can have a flexible computer, which is your DSP processor. You can have it, and you can build this one unit, and then you can put different algorithms onto it to do different things. Whereas before, if you had an analog circuit, you wanted to change from a low pass to a high pass, or change the frequency of some filter, you'd have to change the components, go in there with your soldering iron. Here, you can just download a new program, and everything else is more or less the same. And so it's very flexible and allows you to, maybe use some advantages of scale. Because of the stability and flexibility, you can mass produce these without having to worry about precise manufacturing tolerances. You have to get your silicon right so that your processor is going to work, but beyond that, it either works or it doesn't. It's not like this kind of soft degradation of things in the analog world. And of course, one of the things is that there are entirely new algorithms that we can implement in the discrete domain, which weren't possible in analog domains. So that's good reasons to go digital. The things that we lose are, well, there's this limitation of having to do this discrete-time sampling. You can think of it as the limitations of the analog-digital, digital-analog converter, but it's kind of deeper than that. That even if you keep making better D2As, you've still got a sample representation, which, particularly for very high frequencies, is going to give you problems. The other obvious limitation is that, if I just want to do a simple low-pass filter, I could just put a resistor and a capacitor and, in some order and take it off and I'd be done. Right? That's some kind of low-pass filter. If I want to do the same thing with DSP, I'm going to have a D2A. I'm going to have a processor. I'm going to have an A to D. Other way around. And so there's sort of this minimum complexity that you have to have. And so for very simple things, and in particular, things that you can do well with analog components, you're better off going analog because you can just make it cheaper and make it more reliable. But there's this kind of, there's this intersection of these two curves where suddenly it becomes better to go digital. So, there are some limitations, but basically these things have overwhelmed it, and so we're almost all processing is now in the discrete time domain, which is what we're talking about. So I wanted to play you an example of this, which is time scaling. This is an example of an algorithm that really only makes sense in the discrete time domain. It's not perfectly true, but it's something that wasn't really practical before we had DSP. We've run out of time now. So what I'm going to do is we'll start off with that on Monday. But that's just like, we'll continue this discussion of the basic ideas, signal processing. We'll deal with some definitions, and then eventually we'll be able to get onto some material. Any questions or anything before we go on? If you have any questions about the class, feel free to contact me via email or Darwen. And I'll see you on Monday. Okay, thanks a lot.